Hello everyone, I am Amshi. I am from EC department. My AIT concept beta topic is about Norton's theorem. A linear and bidirectional terminal network can be replaced by an equivalent circuit consisting of a current source IN in parallel with a resistor RN is called Norton's theorem. Here IN is the short circuit current through the terminals, and RN is the input or equivalent resistance of the terminals when the independent sources are turned off. Assume that the network enclosed below is composed of independent sources and resistors. Norton's theorem states that this network can be replaced by a current source shunted by a resistance R. In the Norton circuit, the current source is the short circuit current of the network, that is the current obtained by shorting the output of the network. The resistance is the resistance seen looking into the network with all sources deactivated. This is the same as RTH. We recall the following from sources transformation. In view of the above, if we have the Thevenin equivalent circuit of a network, we can obtain the Norton's equivalent by using source transformation. However, this is not how we normally go about finding the Norton's equivalent circuit. Norton's theorem is an analytical method used to change a complex circuit into a simple equivalent circuit consisting of a single resistance in parallel with the current source. Norton's theorem states that any linear circuit containing several energy sources and resistance can be replaced by a single constant current generator in parallel with a single resistor. Norton's equivalent circuit. The value of this constant current is one which would flow if the two output terminals were shorted together, while the source resistance would be measured looking back into the terminals, the same as Thevenin. For example, consider our now familiar circuit from the previous section. To find the Norton's equivalent of the above circuit, we firstly have to remove the center 40 ohms load resistor and short out the terminals A and B to give us the following circuit. When the terminals A and B are shorted together, the two resistors are connected in parallel across their two respective voltage sources, and the current flowing through each resistor as well as the total short circuit current can now be calculated as I1 is equal to 10 volts by 10 ohms is equal to lambda. I2 is equal to 20 volts by 20 ohms is equal to lambda. Therefore, I short circuit is equal to I1 plus I2 is equal to 2 amps. If we short out the two voltage sources and open circuit terminals A and B, the two resistors are now effectively connected together in parallel. The value of the internal resistor Rs is found by calculating the total resistance at the terminals A and B, giving us the following circuit. Find the equivalent of resistance Rs. 10 ohm resistor are in parallel with the 20 ohm resistor. RT is equal to R1 into R2 by R1 plus R2 is equal to 20 into 10 by 20 plus 10 is equal to 6.67 ohms. Having found both the short circuit current is and equivalent internal resistance Rs, this then gives us the following Norton's equivalent circuit. Okay, so far So good, but we have how to solve the with the original 40 ohms load resistor connected across terminals A and B as shown below. Again, the two resistors are connected in parallel across the terminals A and B, which gives us the total resistance of RT is equal to R1 into R2 by R1 plus R2 is equal to 6.67 into 40 by 6.67 plus 40 is equal to 5.72 ohms. Voltage across the terminals A and B with the load resistor connected is given as VAB is equal to I into R is equal to 2 into 5.72 is equal to 1.44 volts. Then the current flowing in the 40 ohm load resistor can be found as I is equal to V by R is equal to 11.44 by 40 is equal to 0.286 amps. Once again, and using Norton's theorem, the value of current for I3 is still calculated as 0.286 amps, which we found using Kirchhoff's current law, circuit law in the previous tutorials. Norton's theorem summary. The basic procedure for solving circuit using Norton's theorem is as follows. Remove the load resistor RL or component concerned. Find RS by shorting all voltage across source. All voltage sources are by open circuiting all the current sources. Find IS by placing a shorting link on the output terminals A and B. Find the current flowing through the load resistor RL. In a circuit, power supplied to the load is at its maximum when the load resistance is equal to the source resistance. In the next tutorial, we will look at maximum power transfer. The applications of the maximum power transfer theorem can be applied to either simple and complicated linear circuits having a variable load and is used to find the load resistance that leads to transfer of maximum power to the load. Example, using Norton's theorem, find Rn and In of the circuit in shown figure at terminals A to B. To find Rn, set the independent voltage source and equal to 0 and connect a voltage source of V0 is equal to 1 volts to the terminals as shown in figure A. Ignore the resistor 4 ohms because it is short circuited. Also, due to the short circuit, the 5 ohms resistor, the voltage source and the dependent current source are in parallel, hence I is X is equal to 0 amps. At node A, I0 is equal to 1 by 5 is equal to 0.2 amps. Rn is equal to V0 by I0 is equal to 1 by 0.2 is equal to 5 ohms. To find In, short circuit terminals A and B and find the current ISC as indicated in figure B. Note from the figure that the 4 ohm resistor, the 10 volt voltage source, the 5 ohms resistor and the dependent current source are all in parallel. Hence, Ix is equal to 10 by 4 is equal to 2.5 amps. At node A, ISC is equal to 10 by 5 plus 2Ix is equal to 2 plus 2 into 2.5 is equal to 7 amps is equal to In. Another example, find the Norton's equivalent circuit for the network external to the 9 ohm resistors in shown figure. Rn is equal to R1 plus R2 is equal to 5 plus 4 is equal to 9 ohms. Norton current is the same as current through the 4 ohm resistor. To find IN, applying current divider rule. IN is equal to R1I by R1 plus R2 is equal to 5 into 10 by 5 plus 4 is equal to 50 by 9 is equal to 5.556 amps. Norton's equivalent circuit connected with the network external to the network resistor RL. Alternatively, we may determine IN from VTH by RTH. We obtain VTH as the open circuit voltage across terminals A and B in figure C. Using mesh analysis, we obtain I3 is equal to 2 amps, 25I minus 4I3 minus 12 is equal to 0. I4 is equal to 0.8 amps. VOC is equal to VTH is equal to 5I4 is equal to 4 volts. IN is equal to VTH by RTH is equal to 4 by 4 is equal to 1 amps. Find the Norton's equivalent circuit of the circuit in the shown figure of terminal A to B. If we find Rn in the same way we find in the Thevenin's equivalent circuit, set the independent sources equal to 0 as shown in figure 8, from which we find Rn plus Rn is equal to 5, 8 plus 4 plus 8 is equal to 5 by 20 is equal to 20 into 5 by 25 is equal to 4 ohms. To find IN, we short circuit terminals A and B as shown in figure B. We ignore the resistor 5 ohms because it has been short circuited. Applying mesh analysis, we obtain I1 is equal to 1 amps, 20I2 minus 4I1 minus 12 is equal to 0. From the above equation, we find the I2 is equal to 1 amps is equal to ISC is equal to IN. Examples of Norton's theorem.